El Nino teleconnections are severely being impacted by global warming, and El Nino itself amplifies global warming and so on. But nonetheless, there are some very nice reports being put out by even Washington Post and more scientific reporting from the Carbon Brief. Washington Post does a pretty good job as well. So this is the interactive briefing from Carbon Brief. Which is an El Nino explainer, how the super El Nino will reshape the world's weather, assuming that the teleconnections will work as before, as we have seen in the composite teleconnection maps, warm, cold, wet, dry, and so on. These people do a diligent job, and they are careful about saying some people are calling this a super El Nino. There is no official term such as super El Nino. The world is currently experiencing what's expected to become the strongest El Nino on record, dubbed a super El Nino by many. Wow, media has just picked it up. El Nino is the warm phase. We've done all the basics. I'm going to jump ahead. It temporarily raises global temperatures, so adds to global warming. We call it a mini global warming, and obviously reshapes rainfall and extreme weather around the world, impacting lives of billions of people. The current El Nino event began in June and is expected to last into 2027. So the strong El Nino anomalies from the South American coast towards the dateline began to be very clear by June. The El Nino itself was predicted in March, April, which is quite early, but 2023 was also predicted very early. El Nino is part of a wider climate pattern called the El Nino Southern Oscillation. Enso cycle has a cool phase that we call La Nina. As you know, El Nino is the Christ child, so you don't want to use anti-El Nino for the opposite phase, so it's called La Nina. Below, Carbon Brief explains how the Enso cycle works, its impacts on extreme weather and global temperatures, and why this El Nino event is projected to be the most intense since records began. That's important because people have gone back in time and tried to find stronger El Ninos. You can use proxies from corals and tree rings and so on, and you get some ideas, but it's hard to get the amplitude because you get the proxies from nearby are not necessarily covering the Niño 3.4 region, which is the typical index we use. During neutral conditions, you have trade winds blowing from east to west, so southeast, northeast trades meeting in the ITCZ. Waters are pushed westward, so Ekman divergence because of Coriolis. Cold waters come up, upwelling, piling up of warm waters. So these are anomalies. So during a normal year or neutral year, you may not have a very organized anomaly in the Pacific, but now you have a cooling trend in the east and warming trend in the west, and there are always some anomalies around the world because of global warming mixed with local anomalies due to various other features like AMO may be going on and so on. Neutral conditions are basically when trade winds blow from east to west across the tropics, and they are driven by a combination of warm air rising along the equator and the rotation of the earth. Basically, I've discussed details of trade wind mechanisms in my tropical dynamics courses. It's part of carrying the energy northward from surplus energy places in low latitudes to deficit energy places in cold latitudes, and to bring back the winds, you need to come from the north and south, but you add Coriolis and you get the trade winds. Trade winds push warm surface water from South America towards Asia. In its place, cold water is drawn up from deeper ocean off the South American coast, a process called upwelling. When we say deeper ocean, upwelling doesn't go beyond about a couple of 300 meters. It's not deep, but this nutrient-rich water makes the region one of the world's most productive fishing grounds. So South American coasts, Peru, Chile, etc., Ecuador, and even Galapagos is a biodiversity hotspot. Peru is known for its anchovy fisheries. It's largest in the world by volume, and rainfall patterns reflect the surface water temperature. So you can see that you have deep convection in the West Pacific maritime continent into the Indian Ocean, which is generally referred to as the Indo-Pacific warm pool. But the West Pacific warm pool is the one that is separate from the maritime continent, and that's what moves eastward when you have an El Nino. So you have convergence and rising air, and the air hits the ceiling, the tropopause, and then goes east and west and sinks here. So you have the Pacific Walker cell here. So in contrast, cool waters in the eastern Pacific are associated with subsidence and suppressed rainfall. So the South American coast all the way into North American West are all dry regions. The contrast in warm and cold waters is closely linked to a seesaw in the air pressure. So you have cold waters, high pressure, warm waters, low pressure. That's what would be called Southern Oscillation by Walker. He measured it on Darwin, where land gave him pressure, and Tahiti, which is way south at 17 south or so, gave him the pressure as well. But now you have measurements everywhere. So it's a east-west pattern, and that's part of the ENSO for El Nino Southern Oscillation. Southern Oscillation and is tracked by comparing air pressures, Darwin and Tahiti. When an El Nino happens, you have warm sea surface temperatures typically extending from the coast of South America towards the dateline, but we have other flavors like Central Pacific El Nino, which are more focused. Maximum warming, peak warming happens around the dateline, and sometimes you even have cooler temperatures in the east, but typically you have cooler temperatures on the east when you have an El Nino that's associated with suppressed convection and cooling and wildfires, dust storms, etc., droughts, whereas here you will have excess rainfall, floods, landslides, etc. So an El Nino event develops basically with the Pacific trade winds weakening, or sometimes reverse locally on the east, so may become westerlies instead of easterlies. This allows the warm surface water to spread back towards South America, suppressing ocean upwelling. There are more details. Warm water is piled up around here with a meridional structure to it. So the meridional waters tilt towards the tropics, and then tropical waters come in. So it's not just surface waters, they are deeper as well, as we'll see. This reduces the contrast in sea surface temperatures, weakening the air pressure difference across the equator. Further reduces trade winds, what we call the Bjerknes feedback. So strong sea surface temperature gradient, cold, warm, and associated pressure gradients with weak Coriolis can put up zonal winds. But if you weaken the trades, weaken the upwelling, and warm the sea surface temperatures, then the pressure gradient weakens, winds further weaken, upwelling further weakens. This is a positive feedback that's called Bjerknes feedback, because Jakob Bjerknes was the one who first discovered it, as we'll see in a minute. So the feedback loop obviously has to end with something, but when you bring the warm waters here, you have suppressed upwelling, and you have deep convection that's moved from here to here. So you anomalously dry conditions happen here. Already we have serious drought happening over Indonesia and Western Pacific, for example. And the anomalies here, the scale is -5 to 5, but this El Nino is going beyond 2 degrees C, is expected to grow maybe up to 3 degrees C or stronger. This is why it's being called a super El Nino, which is not necessarily a scientific terminology, as I said. So as the warm water shifts, so do the rainfall patterns, because warm surface temperatures are needed for deep convection in the atmosphere. So that brings rain, etc., to South America, even in North America, but later in the winter. So December, January, February is when the El Nino peaks. The shift in winds over the Pacific also has knock-on impacts for weather around the world. Basically, trade winds change, entire Walker cell changes and the heating moves, so that heating can send off waves and set up meridional wind changes. So Hadley cell also changes, and the knock-on impacts, as they're called here, can go global, and that's what we call the teleconnections. The opposite phase, La Nina, develops during a La Nina event. Basically, trade winds get stronger, upwelling gets stronger, warm pool gets stronger and crunched more towards the west. You get a systematic cool warm pattern, and of course you have stronger convection here, more suppressed convection but more production, fisheries, etc. on this side, and you see the increased upwelling of cold water, warm air, and stronger convection here, as seen with the bigger bunch of clouds here. So La Nina amplifies rainfall patterns seen in a neutral year, bringing heavy rainfall or heavier rainfall to Southeast Asia and cooler and drier conditions to the west coast of South America here. The history is that, of course, Gilbert Walker, who was in India with the East India Company in the 1920s, was curious about the monsoon famines. He was in fact bothered, and he wanted to make predictions. So he went around looking for all the signatures, and he found Tahiti and Darwin, and saw that they have an out of phase oscillation, and whenever it was in its positive phase, so when Darwin was higher and Tahiti was lower because it was warmer here and colder here, El Nino happened. He didn't call it El Nino, he didn't know at the time, but he saw that that related basically to a drought in the monsoon. So the cycles of El Nino and La Nina have been affecting Earth for millennia. A study of proxy data from preserved corals that I mentioned before suggests that El Nino-like variability has existed for at least 130,000 years. Before that, we had the previous, I think it's the Eemian, where we had an interglacial like we are in now. The last glacial started to grow around 130,000 years ago and became its coldest in about 21,000 years ago, and then we started to come out of it, and Holocene started about 10,000-12,000 years ago, right? So historical records suggest that Peruvian fisher folks had recognized El Nino events by at least the 1600s, when warm southward flowing current would replace normally cold, nutrient-rich waters. They called it El Nino the Navidad, or the Christ child, because it was most noticeable around Christmas, and they thought warm water is a blessing from God if you wanted to go swimming in the waters, even though it brought dead fish and dead birds and was not good for business of catching fish. In 1926, British scientist Gilbert Walker coined the term Southern Oscillation, and I already mentioned it. In the 1960s, much later, Swedish-born meteorologist Björknes Jakob Björknes, joined the dots between El Nino and the Southern Oscillation, establishing the concept of ENSO, or El Nino Southern Oscillation. And we define its strength basically with some coastal boxes, Niño 1 plus 2, a more eastern box that was originally used called Niño 3. As more data became available, people moved the box to the middle, called it Niño 3.4, because there was already a Niño 4 that was defined for the central western part, and this more diligently or more completely represent the El Nino, even though now we have El Nino flavors, which means the warming is more here, less here, sometimes coastal warming doesn't happen, and so on. So defining the strength of an event depends on these indices, and Nino 3.4 is what is being used now to talk about the super El Nino. Typically, they focus on Nino 3.4, as you can see here, going from 1950 to about 2026 already. So we had the 23-24 El Nino, 15-16 was quite strong, 82-83 was strong, 87-88 was the strongest in the 20th century, and so on. And other regions used, as we said, are these that we already mentioned. Now so this is Nino 3.4 is called ONI Index, Oceanic Nino Index. Traditional Oceanic Nino Index tracks how far how far conditions in Niño 3.4 depart from average on a 3-month running average. You cannot have blips of warming. It has to remain warm above half a degree or so for several months for it to be called an El Nino, and minus 0.5 degrees for several months to be called a La Nina. Different organizations have slightly different criteria for declaring El Nino and La Nina when they are underway, but when it is in full bloom, everybody can see it. And we have been looking at the impacts in terms of the teleconnections, as I mentioned. So impacts of an El Nino event, these bluish colors are wet, the lighter blue colors are cool, and so you have wet and cool conditions across southwest to southeast US. California gets a lot of winter storms, for example. In the meantime, this region of the US can get warm and no precipitation signal as such, but here dry droughts are relieved by El Nino and so on, but already there are papers arguing that this teleconnection has begun to change, likely because of global warming. Indian monsoon deficit is always the big news, but only about 60% of the deficit years are directly related to El Nino and so on. So there are always some details. And we said the convection shifts from here to here. You end up with this dry region, especially over maritime continent. The wildfires and dust storms in Australia are very famous. Even the beer consumption in Australia goes up because of the hot, dry weather. And you have mixed dry and warm conditions here. These also have seasonality. They haven't put the seasonality here. Indian monsoon, for example, happens in June, July, August, and there are other signatures that happen in other seasons of the El Nino year. Okay, so this is El Nino over Southeast Asia and South Asia. So you take the global map and look at it part by part. So South Asia and Southeast Asia experience strong impacts from El Nino. Central and South America, El Nino typically brings warmer, drier weather to northern and tropical parts of the continent and heavy rainfall to the south. Okay, I hope I'm not screwing that up, but you see the Southeast Asian signature here, warm, dry, and all the wetness is moved to here. And Brazil, Argentina, Brazil gets a huge signature, Argentina gets some, here parts of Central and Northern South America also get signatures. So this is just partly focused on south. So in Central South America, El Nino typically brings warmer and drier weather to the northern and tropical parts, as we said. The changes in conditions means that countries such as Colombia, Venezuela, and northern Brazil face a higher risk of drought and wildfires, while southern Brazil, central Chile, northern Argentina often experience severe flooding. But as I said, global warming appears to be tinkering with all these. In Southeast Asia and parts of Australia, El Nino usually brings drier conditions. We are looking again more focused here, raising the risk of severe drought and wildfires. Okay, warm conditions December, February, June to August. This is July to June to September. Months are put here: December, February here, December, February here, June, September here, October, January here, and so on and so forth. Okay, throughout the year, throughout the globe, there are teleconnections. Okay, so El Nino Africa, this the Sahel region, West African region, July, September shifts, wet conditions on eastern part during October to January. December, February, you get dry conditions. And remember, December, January, February is when the warming peaks typically. Almost always. And this is for North America, so December, February, and December, February, as I mentioned already. El Nino brings in North America milder winter temperatures to Northwest and Canada and the US, while increasing winter storms and flooding in southern states and California here. Okay, tropical storms are affected, the most famous one being here reduced hurricanes, because El Nino causes a stronger vertical shear. You also get suppressed storms on this side, but typhoons see a bump up, and tropical storms, just looking at the hurricane season, you get a quieter season. This year, in fact, has been true to this so far. In the third week of August, no named storms and hurricanes making landfall, and so on. North America and the Caribbean, El Nino can lead to quieter Atlantic hurricane season. In the North Atlantic Ocean, tropical storms are called hurricanes, as we know. This is because the El Nino's impact on atmosphere and ocean conditions can increase vertical wind shear in the tropical Atlantic and Caribbean seas. These powerful winds tear apart developing storms, vertical shear suppressing the development of hurricanes. Tropical storms here, more intense storms on the eastern side. So here, quieter season. El Nino tropical storms, typhoons get more intense. In fact, this year has been a bumper season, and even the North Indian Ocean can get more cyclones. But remember that here we have a pre-monsoon season and a post-monsoon season. Not much happened in the pre-monsoon season of 2026. We have yet to see what will happen in October, November, December of this year, whether we'll get more storms and so on. In other parts of North America, including southern U.S. states and California, El Nino can bring more intense winter storms. This is due to El Nino's impacts on the jet stream, a current of fast-flowing air up in the atmosphere affecting weather in the mid-latitude regions. In fact, there are papers showing that subtropical jet stream and subpolar jet streams both bring, so-called Hawaiian Express moisture pumped into California during winter months, produce massive snowstorms or even rainfall and so on, and they are always on watch when an El Nino comes, but these teleconnections may be changing as well. Okay, during El Nino, the weakening of the trades causes warm water from Western Pacific to shift eastward. This also shifts the area of tropical storm formation to the east. In Asia, the eastward shift means the tropical storms known as typhoons in this region are less likely to move towards the Philippines, are instead more likely to affect China, Japan, and South Korea. So there are slight shifts, but internal variability is high, so this doesn't happen in every El Nino. Because of the eastward shift, typhoons typically have longer to travel before making landfall. This gives them more time to gather heat and moisture, increase their chances of becoming major destructive storms. There are some details. More recently, the number of typhoons don't change much from El Nino to La Nina to normal years, because it turns out the wind stress curves can change the heat content in the ocean, which tends to determine whether tropical storms become tropical cyclones, because that energy is needed, and so on. For islands in the central and eastern Pacific, such as Hawaii, Kiribati, and Tuvalu, the warmer sea surface temperatures can bring more frequent and intense tropical storms. For islands in the central and eastern Pacific Oceans, such as Hawaii and Kiribati and Tuvalu, the warm sea surface temperatures can bring more frequent and intense tropical storms. In fact, Hawaii got hammered by a very strong cyclone storm, whatever it was called. Okay, so let's see how long I have gone. Maybe I need to split this into, this is already 22 minutes. So let's come back and try to finish it. Well, I just have a few more. Maybe I'll just plow through it. Okay. La Nina is not exactly opposite of El Nino. There's an asymmetry. So impacts of La Nina event, you can see monsoons tend to be stronger in Southeast and East Asia. West Pacific, Eastern Indian Ocean, Maritime continent tend to be wetter. It's drier on this side and colder. And you also get wet on West African monsoon, Sahel region, some dryness here in Central East Africa, and wetter in Southeast Africa. Namibia has a strong signal in El Nino. So here you get Japan gets a strong signal. Australia, these Great Barrier Reef region, Solomon Islands, etc. get all the other islands we mentioned also get some signature. Cool here, drier here, wetter here, and cooler here. So they are not always opposite of El Nino. That would be the main point. So you also see the global teleconnections. So La Nina, Southeast Asia and South America, just putting them together, Colombia, Venezuela, northern Brazil, and Southern parts of the continent, such as southern Brazil, northern Argentina, etc., also see severe dry conditions. Risk of droughts go up. In Southeast Asia, Northeast Australia, La Nina is associated with above average rainfall, often driving severe floods and landslides. Africa, you can see the West African monsoon signature. Drier conditions here in East Central Africa, as I mentioned. This is in December, February, and Africa, of course, can bring increased rainfall and high risk of floods in southern parts of the continent from December to February, etc. North America, somewhat opposite. So instead of wetter, you have drier conditions, and you have cool, wet conditions over here during December, February. This also dry, warm during December, February. Okay. El Nino obviously bumps up the global temperatures. As we said, La Nina can temporarily boost or dampen. El Nino and La Nina can temporarily boost or dampen global temperatures respectively. So La Ninas are seen as dips in the global warming trend curve here. El Nino of 97-98 clearly seen. 2015-16 clearly seen. 23-24 raised a lot of 23-24 raised a lot of debate about whether we crossed 1.5 and so on. Unfortunately, it depends on the data set you are using, and there are other issues to deal with. Okay. In general, a 1 degree C temperature shift in the Niño 3.4 region is associated with around a 0.1 degree C change in global average temperature, with a lag between 3 and 6 months. So the ocean heat content gets released over time, and the atmospheric warming happens over that time as well. As a result, major El Nino events have contributed to record-breaking annual global temperatures, including 98, 2016, and 2024. So 23 was the El Nino, 24 gets warm, 97 was the El Nino, 98 gets warm, 26 is an El Nino, 27 will be warmer. Okay. Similarly, La Nina will have a cooling impact. The global temperature record with the influence of El Nino and La Nina removed, you can see that if you remove it, the differences are clearly visible, as we pointed out before. El Nino and La Nina are generally the largest drivers of year-to-year variability in global temperatures, but this influence is only temporary. Essentially, ocean is collecting heat during normal and La Nina years in the Eastern Pacific, where cold waters come up. Atmosphere tries to put heat into the ocean. That heat gets taken into the ocean, hangs around in the west, and in the tropical regions, thermocline gets deeper, and that heat gets belched out during an El Nino, and more heat goes into the ocean during a La Nina. Ongoing human-caused warming has meant that new global temperature records set in El Nino years have typically been short-lived. ERA 5 temperature data set, for example, 98 was a record warm year at that time, but it was subsequently topped by 2005. So 2005 was not a strong El Nino, but global warming came back. That record was then surpassed in 2010, which was then eclipsed by 2015, which was an El Nino. And 2016 was the following year, which got warmer. 23 was El Nino, 24 was the warmest so far, but 26 and 27 are probably going to get past that. ERA 5 temperature data set, why did I put that again? Removing the influence of El Nino and La Nina from the global temperature record highlights how these events can cause more severe peaks and troughs from one year to the next, but ultimately human-caused climate change is the key driver behind record-breaking global temperatures. But you have to be careful, because now what's happening in Europe in terms of the repeated heat waves and the combined drought, creating real havoc, wildfires, etc., is, I think, a combination of El Nino and global warming, because global warming moves the jet stream, melts the Arctic ice, which have impacts on European warming, which is warming quite rapidly compared to global warming. And El Nino doesn't have a direct teleconnection, as we saw already in this series of slides, but when El Nino added to global warming, we have what 2026 is seeing in Europe, right? So global warming is a key driver. If El Nino bumps up global warming, then global warming impacts are likely to get amplified as well. So here we come back to 26-27 super El Nino. Model forecasts suggest that the current El Nino will be the strongest in modern records. The Oceanic Nino Index forecast from dynamical models, there are many forecasts, but they are all having different levels of warming being predicted, and here something is being shown. So this is where we came out of a mild La Nina in 25, and we got rapidly warm in the spring of 26 because of some things called westerly wind bursts, which have then pushed the warm pool eastward and made it warmer and warmer. Trades are weaker, and forecasts into October, November, December are showing here maybe up to 4 degrees C, but some of them are below here, closer to 3 degrees C. Some show earlier demise, some show later demise, and the range is quite high going into the following spring. Often you get a rapid transition to La Nina, but here all the way into spring, nobody is showing negative temperatures. So Earth is currently experiencing an El Nino event which began in June and is expected to last into 27. Many forecasts suggest that this El Nino could be the strongest on record, causing severe impacts globally. Because of this, many media outlets and commentators are calling this event a super El Nino, although this is not a recognized scientific term. Carbon brief analysis of forecasts from 14 different modeling groups that track El Nino globally, updated with the latest data, finds that 96% of runs predict that this event will be the strongest in modern observational record. This means that models predict that peak sea surface temperature anomalies in the Niño 3.4 region will exceed the previous record of 2.75 degrees C set during the El Nino event of 2015-16. 23-24 didn't get as strong, but I've discussed already how 23 is supposed to be an ocean dynamic El Nino, didn't couple strongly to the atmosphere, and that stochastic white noise or multiplicative noise forcing was not there, which is very strong this year and was also strong in 2015. An anomaly is the difference between current conditions and the long-term average. So the chart shows forecasts made. How might climate change affect El Nino? Possible super El Nino forecast for 26-27 has been renewed with this El Nino, there has been renewed interest in whether climate change is making events more likely. We read the New York Times article interviewing many scientists on this, and basically the answer is vague. We don't know. It's not, because we have very small samples, it's not clear. It's very hard to say that we are beyond the internal variability in terms of the strength of the 26-27 El Nino that's expected. The potential influence of climate change on is an area of active scientific debate. The latest assessment from IPCC published in 2021 said that the intensity of El Nino along with frequency of high magnitude events has increased since 1950. We saw that paper by led by Wenju Chai, and this is when compared to the periods in the past stretching all the way back to 1400. However, proxy data for Earth's past climates from tree rings to sediment cores show that El Nino events have varied wildly in their frequency and intensity over the past 11,000 years, making it difficult to attribute the recent changes to human-caused warming as of yet. The uncertainty also makes it difficult to assess how El Nino events could change in the future. One study from 2017 projected that El Nino could double in frequency at 1.5 degrees C of global warming, the aspirational temperature target for Paris Agreement, and that's why there is always a debate about whether we crossed 1.5 C. More recently, in June 2026, the New York Times spoke to 16 climate scientists, I already included this in one of the podcasts, about the likelihood of warming influencing ENSO cycle, of which 8 said they see compelling evidence that climate change is likely to increase the intensity of El Nino events. I kind of rushed through it because this is repeating many of the things we have discussed in this series of podcasts already, but it's still put together very nicely, so I wanted to run through it. It's a very readable, very nice interactive graphic article. I cut and paste each one, so you can't see the interactiveness here. You cannot print those, so you have to sit and do cut and paste. But nonetheless, I found it to be very useful. I hope you do too. Okay, see you next in the next El Nino podcast.